Welcome, everybody. Welcome back to the third day of this this very interesting and wonderful workshop. We talked about the test of general relativity and the classical aspects of black hole. So now the agenda for today is to go beyond general relativity, and Paolo is gonna start taking us in that direction. Paolo, take it away.
Okay, thanks very much, Nayesh. And let me thank Luca, Raul, and Francesco for this kind of invitation. It's really a pleasure to give this seminar. So as Nayesh was saying, I would discuss a particular aspect of, say, modified gravity and how to test modified gravity, in particular, how to test the black hole paradigm, which is looking at the ring down of black hole microstates that arise in certain string theory scenarios. And well, I will discuss more later, and hopefully I will illustrate how these plots come about. Okay, so as an introduction, many of you are in the field long enough now to remember that just say 10 years ago, black holes were not so popular. Nowadays, they are everywhere instead. We have detected them in different mass ranges, from stellar mass to supermassive, with different probes, electromagnetic and gravitational waves, and they were awarded at least 2 Nobel Prizes. Maybe there will be other in the future. So the question is, why testing the black hole picture, since it has been so well already probed? And in fact, there are many motivations to do that, and I list here just a few. So one is the fact that there might be other species of compact objects other than black holes and neutron stars in the universe. And in this sense, for example, the surprising mass gap events, both in the lower mass gap and in the upper mass gap, that LIGO Virgo had detected recently, might be explained with some alternative to black holes and neutron stars. We still don't understand very well the seeds of supermassive black holes at high redshift, and there might be objects made of dark matter if there is dark matter in the universe, for example, boson stars, if there is a bosonic field. There are more theoretical motivations that maybe this audience is more interested about, and they are related with the information loss paradox that we'll be discussing in the next few days, the problem of singularities within black holes, the instability of Cauchy horizon, etc. And these problems might be related only to, say, Planckian physics, but there are several proposals that try to solve these issues. While trying to solve these issues, also modify the horizon structure quite dramatically. And there are several proposals, firewalls, non-locality, or what I will focus most in my talk, the fuzzball proposal in string theory, which replaced the horizon by a regular horizonless compact object. And the point I would like to make is that many of these approaches might be actually bold and very speculative, but we are currently in a position to test them, at least to some extent. And in the future, we are not going to do much better than now, in fact. And therefore, if we don't test them now, when? And finally, if you are really agnostic, one motivation could be just that we want to quantify the black hole-ness of various astrophysical sources across different mass ranges. For example, to do a Bayesian model selection between a black hole and any alternative. And it goes without saying that any alternative to a classical black hole will either imply new physics or new matter field. So it will really be a major discovery. So what is a black hole? So for the purpose of my talk, I will be very naive, I would say, and also agnostic in defining a black hole. And for me, it would be an object whose surface at a certain location is a perfect absorber. So we can imagine a two-dimensional parameter space. One is the reflectivity, so how much energy is reflected at the horizon. The other one is, say, the compactness or the radius of the object. And I'm parameterizing these in terms of R plus, the Kerr horizon, plus an epsilon, which is some correction. And in this diagram, a black hole, classical black hole in GR sits here. 0 reflectivity is a perfect absorber, 0 epsilon because, well, it's a Kerr black hole. In this diagram, there can be different corners: small compactness, no absorption; large compactness, large absorption. And of course, as you can imagine, the closer you are to this, to the origin of this diagram, the more difficult it will be to test the paradigm, because all observables should be similar to the black hole one. In this diagram, it's very important, this region here, when epsilon is over the unity, because it discriminates between objects with or without a light ring. This will be very important. And if one is interested in features such as corrections at Planckian scale away from the horizon, this epsilon is of the order 10 to minus 40, depending on the mass of the black hole. But anyway, there is a huge jump in orders of magnitude between this regime and this other one. And of course, the question is how do current and future observations constrain this parameter space? Okay, a few words on the fuzzball paradigm, because I will be focusing on it later on. So in this paradigm, classical black holes are interpreted as an ensemble of a huge number of regular horizonless microstates geometries that at classical level arise as low energy solutions to some low energy truncation of string theory. And there is really a huge number of them, which hopefully can explain the huge entropy of the black hole. And this was indeed the case for some very specific configuration. So the picture you can have in mind is that a classical black hole is interpreted as really the ensemble of these microstates. All of them can be very deformed. They do not have an horizon, and the horizon emerges as a sort of a coarse-grained description of these regular geometries. A very important point of this proposal is that, well, first is well motivated in terms of theories behind, and second, the mass is a free parameter. So this approach can explain both stellar mass and supermassive black holes, which is not typically the case in other approaches. The cons are that typically these solutions are very complicated. Most of them are describe only quasi-extremal or extremal charged black holes, even though recently there has been extension to non-supersymmetric solutions. And well, anyway, there has been a lot of development in this at theoretical level in this field. I can recommend this review by Daniel Meyerson, which I think is very nice, both from the point of view of the theory and from the point of view of the observations of the fuzzball proposal. So I will focus on gravitational wave based test of classical black holes. And the picture you can have in mind is that of the standard coalescence, spiral, merger, ring down. And at each of these stages, and in all of them essentially, there might be differences whether there is a classical horizon or not. For example, there can be tidal effect in the spiral that deforms the object, or the multipolar structure can be different. There can be absorption by the horizon itself during the spiral. The merger can be very different, the ring down as well, and there can be post ring down features, for example, echoes in the waveform, and I will focus mostly on the post merger phase. Okay, so let me just briefly review black hole spectroscopy. So the standard paradigm is that the post-merger signal can be approximated as a superposition of quasi-normal modes of the remnant. So these are damped sinusoids, a frequency and a damping time. And even tholl LIGO and Virgo have detected a few events for which the dominant quasi-normal mode has been measured, only in the future we'll detect a lot of events with 3G detectors and LISA of order 100,000 per year, allowing for black hole spectroscopy. So meaning we can detect several modes and try to do non-trivial tests on this. For example, we can constrain deviations from the standard Kerr quasi-normal modes that depend only on the mass and spin, or detect extra ring down modes, for example, due to extra polarizations or matter fields. And well, recently, a recent development is that overtones, which are, say, the higher harmonics of a given angular mode, can also be used to perform this test, and this will be very important in the future. Okay, so why are quasi-normal modes so important to test the horizon? The reason is that, well, from a more mathematical point of view, quasinormal modes are the poles of the Green's function in the complex plane of a given equation of this form, which is a typical Schrödinger-like equation with an effective potential. In this coordinate, the horizon is at -infinity, and plus infinity is, well, the space infinity. And the maximum is due to the photon sphere of the black hole. So these quasinormal modes arise by imposing outgoing boundary conditions at infinity and purely ingoing boundary conditions at the horizon, just because, well, classical horizon is a perfect absorber. An important point is almost trivial, but it's important to remind, is that radiation takes infinite coordinate time to reach the horizon in this coordinate. And this already tells you that the boundary conditions at the horizon cannot really be a discriminator because, well, in principle, perturbations take infinite time to get there. And in fact, what I will show is that the quasinormal modes are mostly related with this photon sphere barrier rather than the horizon boundary conditions. And an important point is that the moment you sort of modify the classical horizon picture in any way, it can be, I don't know, a regular stellar-like interior or matter, maybe collapsing matter, or fuzziness of the space-time, or modify gravity, and for example, look at some paper on this. The moment you modify this, you will change in some way these boundary conditions at some point here close to -infinity, and therefore completely change the eigenvalues of the problem. In particular, there can be, actually there will be anyway, trap modes within this potential barrier and whatever is in the interior. And I mean, we maybe don't know it because it's model dependent, but definitely there will be some radiation coming back from -infinity, because if it does not come back, that will be a classical horizon. And in fact, so if you take one of these models and compute the quasinormal spectrum, what you will find is that in the black hole limit, so when that epsilon parameter goes to 0, the quasinormal modes, these are the quasinormal modes of a given model, diverge in comparison to the quasinormal modes of a Schwarzschild black hole, which are up here. So they become more and more different from the quasi-normal modes of a Schwarzschild black hole. So the spectrum changes dramatically, but the important point is how about the ring down. So in order to understand this better, in a more sort of generic way, what one can do is to use the membrane paradigm, the black hole membrane paradigm, and actually extend it to accommodate exotic compact objects. And this was done in these papers here. And the idea is that in the black hole paradigm, one can replace the horizon by a fictitious viscous membrane with a viscosity, with a shear viscosity parameter, eta black hole, equal to 1/16 pi. If you don't impose this condition, so eta is a free parameter, you can model different situations, so different objects, for example. So again, it's a two-dimensional parameter space, epsilon, the compactness essentially of the object, eta, and a black hole, in this case, sits up here on the left because epsilon goes to 0. What I'm showing here is the relative difference between the quasi-normal modes of a black hole and that of this object in this parameter space. And as you can see, the difference can be 20, 10%. So all this area is already excluded by the measurement of GW15 on 914, which was in agreement with the black hole value. The only region that is not excluded is this gray region here, which anyway could be excluded if the SNR is increased by a factor 10. So in the 3G era, or in the LISA era, it would be possible to essentially rule out completely this region just by a single observation. You might ask why cutting this plot at epsilon 10 to -2, and the reason is that if epsilon is smaller, radiation takes longer time to probe the boundary, and this is the reason why the prompt ring down will be the same as that of a black hole. So this initial ring down that one observes in a classical black hole merger is actually not directly related with the horizon, but is just a property of the light ring. What is important to have a classical horizon is that the signal dies off completely afterwards. If there is some reflectivity instead, part of the radiation goes back. And probably the interest in this the majority of interest in this is due to the fact that the delay time between this radiation that goes back and then goes back and forth within the potential barrier of the object scales logarithmically with this epsilon parameter, which means that even if epsilon is 10 to minus 40, as I was mentioning before, this delay time is not huge, it's something that can be probed. And in fact, well, there has been a lot of modeling about this effect recently. And what you can see is that these echoes that are repeated signal of the former prompt ringdown, which are modulated and refiltered by this barrier, are separated by a logarithmic in epsilon term. And the picture you might have in mind is that the photon sphere and the surface interior of the object reflects the barrier, and each time an echo is filtered by this barrier, by this reflection coefficient, and by the black hole reflectivity and transmission coefficient. So how about detectability? There has been several studies and contrasting results about the detection of this effect in LIGO data. The most recent analysis using O1, O2, and O3A data did not find any combined statistical evidence, but there is still work going on. And what is interesting is that there are currently echo search pipeline, which are now routine in LIGO and Virgo, in the LIGO Virgo collaboration. So these effects are essentially now probed for most of the events for which the ring down is accessible. At the same time, this has required a lot of progress in the echo waveform modeling. I can suggest this review by Abedi, Nayesh, and collaborators, which sort of summarize all the challenges of these searches and modeling. I can just mention that current searches in LIGO and Virgo use very simplified templates, and in fact, the whole story is much more complicated. The reason is, even within a toy model, very simplified one, perturbation theory, so something very simplified, the echo morphology can be very complicated. What I'm showing here are two polarizations of the gravitational waves for a system which is linearly polarized in the black hole case. So in the black hole case, you just have one polarization. What you see here is that depending on the spin of the remnant and the reflectivity coefficient, which might, by the way, could be frequency dependent as well, you might get mixing of polarization. Sometimes, as in this case, you don't get echoes because there is interference between them. So it's very complicated. And still, this is a toy model. So it's important to understand this. So to go beyond this state of affair, what we did recently with Taishi Ikeda in Rome and a group of string theories in Rome, Tor Vergata, the other university, was to study the ring down of a black hole microstate. So one of those solutions I was mentioning before that emerged in the fuzzball paradigm. So the problem is very complicated. So we started by the simplest case. So taking a background geometry, which is one of these solutions of n equal to supergravity, and study the 3+1 evolution of a Klein-Gordon test field. So it's an extra scalar field on this microstate. The point that makes the things complicated is that this microstate does not have any spatial isometry. So in general, it can be arbitrarily deformed in a way that is, well, very different from Kerr in principle. And this, of course, makes the problem tractable only numerically with a 3+1 evolution code. And well, we focus on these specific geometries, but in fact, the method works for any geometry that is stationary. Another important point of this geometry is that they do not have by construction an ergo region, so they do not suffer by the ergo region from the ergo region instability, which will make them unstable when rotating. So these solutions are rotating, they have angular momentum, they do not have an horizon, but they do not have an ergo region as well. So they are, in principle, they should be stable. So here are some details of the ansatz of these solutions. It's complicated, but one can interpret it in terms of n centers. In fact, these are called multi-center solutions. There are n centers that, for example, in this geometry are on a triangle. On this geometry, they are on a line. And when the centers collapse to a single point, you recover the black hole solution. Okay, so here are the results. These are simulations made by Taishi. So what I'm showing here is different time snapshot of first row, the black hole ring down, second row and third row are these two fuzzball configurations. And for the same initial data, the initial data is a spherical pulse close to, say, the origin. And you can see two features. So the first one is that you see the black hole starts ringing down in this spherical mode that exists only because there's a scalar field. Of course, there are no spherical gravitational waves. And it dies off very quickly because it's a damped sinusoid. In the fuzzball case instead, first of all, you start with something spherical, but then it develops structure because the background is not spherical symmetric. Second, even after a certain amount of time, you still see signal because as you expect, the pulse dies off much less. I mean, not as fast as in the black hole case. I can show you a movie of this animation. So this is taken from our webpage. Let me play this one for you. And so what you will see is a slide of on the y=0 plane of this ring down. And what you can see, well, first of all, you see that something that was spherical develops some structure. As you can see here, there is this dipolar structure and then quadrupolar, etc. And most importantly, look at the time scale. There is still signal at very late times, which will not be the case in the black hole. So this ring down lasts much longer than in the black hole case. So to understand better what's going on, you see after 1000 m, this is in unit of the total mass, is still going on. So let me show you exactly what's going on here. Here I'm showing the signal decomposing spherical modes and quadrupolar modes, L=2, M=0. These two are the black hole case. As you can see, there is a standard ring down, then there is the power law tail, the price tail, and this is the standard picture. It dies off in quasi-normal-mode ringing. Here there is a 1-1 mode just because, as an example, we started with a dipolar initial data. And because of the spherical symmetry of the system, if you start with L=0, there is only L=0 for black hole. If you start with L=1, there is only L=1. In the fuzzball case, it's different because here we are starting with a spherical mode, and you see that there is both spherical modes, L=0, but also L=2, that are triggered by the non-sphericity of the spacetime. Then you see that the mode dies off exponentially initially, but then there are repeated signals, and in fact, it dies off much less faster. And in some cases, well, it dies off really slowly, like in this case here. And there are repeated signals again here. So you see that there is clearly more structure. There is some repetition, like in the echo waveform that I was showing before, but there is also mode mixing, and the signal is much less clean than in the usual sense. So this is the price to pay to go from a toy model to something that is more realistic, but also much more complicated to deal with. And as a bonus, even though this is just a test scalar field, from our simulation it's clear that the geometry is stable dynamically under at least this field, even though this geometry has angular momentum, as I was saying. We don't know yet the gravitational case, but at least for a test scalar field, the perturbation dies off, even if not fast, not very fast. We also check that the quasi-normal modes in the black hole case, so these black holes are not Schwarzschild, they are charged black holes in this theory. The quasi-normal modes extracted from the code agree with frequency domain computation and also with the aconal approximation, so the geodesic approximation from of these modes, which is easy and analytical. And in fact, the approximation works pretty well even for L=1, which in principle should not be the case. What I'm showing here are, in fact, the aconal approximation of the quasi-normal modes for the fuzzball and for the black hole for different fuzzball configuration, and this capital L is the distance between the centers. So when L goes to 0, you should recover the black hole limit, And in fact, what you see is that the quasi-normal modes, for example, in this line here, agree very well with that. Oh, sorry, this one and this one agree pretty well with that of a black hole. So in the L equals 0 limit, the quasi-normal modes that are essentially this prompt ring down here are the same as that of a black hole, but still you get different behaviors later on because radiation is not absorbed by the horizon, it's just reflected off this complicated potential. Yeah, maybe this is a bit technical. If you want, we can discuss it later. These geometries are singular from a 4-dimensional point of view. They are regular in 5D, but when you compactify to 4D, the centers are singular. In order to cure this singularity, we use a sort of cutoff given by this epsilon parameter. This epsilon, sorry, is not the same as the epsilon I was mentioning before. It's just a regularizator. And as you can see, the smaller you take this number, the more the signal converges, say, to the true value. So this is a check that one should do to make sure that the solution is physical. And also, well, we check numerical convergence for the simulation, at least till the time I was mentioning, we have numerical convergence, so even after a very long time. Okay, so I don't know how much time do we have?
I think it's 5 minutes.
Okay, good. So in 5 minutes plus questions, right? I don't want to.
Yes, and then there are 5 minutes per question. So 5,
okay.
10, yeah. Mm-hmm.
Okay, great. Okay, no, yeah, I will take just a few minutes because so I show you this diagram here. These are in fact embedding diagrams of these fuzzballs, but I didn't explain them. So let me actually spend some time on the multipolar structure of fuzzball, which is interesting on its own. And it's interesting for various reasons. One is to draw those nice embedding diagrams. The other is because the post-Newtonian waveform depends on the quadruple moments and higher moments of the two objects in the binary. In particular, the point particle phase at second p-n order depends on the multiple moments. For a Kerr black hole, we know that the multiple moments, mass moments, and spin or current moments are satisfy this elegant relation. So they depend only on mass and spin, in fact. And also, because of the equatorial symmetry and the axis symmetry of the Kerr metric, well, there are some moments that are exactly 0. So a Schwarzschild black hole can be visualized as a sphere. A Kerr black hole would be, well, I'm exaggerating this, but it's a sort of deformed object with many moments. And the color scheme I'm using here is for the current moment. So the shape are the mass moment, the colors are the current moment. For exotic compact objects, we might get corrections to this. So there might be deviations from the Kerr multipolar structures. And interesting enough, under certain assumption, in particular that GR works pretty well near the horizon and there are no divergences, there is a sort of hair conditioner theorem that tells you that these corrections goes to 0, must go to 0 sufficiently fast, either linearly in epsilon or logarithmically, again, there is this log, if they are spin induced. So the ones that are proportional to the spins diverges goes to 0 very slowly. And this again is a way to test these corrections, because in principle, from future observation, we can put important constraints on these quantities here. Well, if you're interested, we built a lot of solutions with all these moments, so you can find very weird. These are all solutions within GR, vacuum solutions with generic multipolar structure, and these were work done by Guillermo Raposo during his PhD in Rome, and they are freely available on our webpage. But yeah, in my last slide, I want to discuss the multipolar structure of fuzzballs, because that is very peculiar. And in fact, as I was saying, fuzzballs do not have isometries, spatial isometries, so they can break equatorial symmetry. For example, you can have an S equal 2, so a quadrupolar current moment, or an M equal 3, an octupolar mass moment, which are 0 in Kerr. And they even break axial symmetry. So actually, we don't have a single number like M2, but we have, in fact, a tensor that has, say, 5 components for the L equal 2. So there might be M20, M21, M22. And the net result is that if a Kerr black hole has this shape, a fuzzball is both deformed in the mass moments, but also in the current moments. And well, it's the multipolar structure is much richer. In fact, there are certain multipolar ratios that are universal. This was studied in this series of paper here. And in general, well, there has been a lot of interest in this topic recently. As you can see, all these references are from, well, are less than 1 year old. So for sure, there will be interesting developments in the future. An important point would be to develop waveforms that include these effects. We are currently working on it, because in principle it can be a way to distinguish fuzzball from black holes from the in-spiral part only. Okay, so conclusion, we are really living the black hole era right now. There are plenty of discovery opportunities for new physics, and I think the black hole microstate phenomenology is now in full blossom, which is great. There has been a lot of development recently. It's definitely more complex than many toy models studied in the past, but by understanding it better, we should be able to put interesting constraints. From those of you interested in quantum gravity, maybe quantum gravity effects are out of reach, but if they are not, horizons, event horizons, would be very important to look for them, because, well, they are special in many ways. They might be a portal to observable effect. There is a long way and several open issues when confronting fuzzball with data. If you want, we can discuss them in the discussion session. From the, say, practical point of view, we need dynamical simulations of these solutions, not only, say, the test fields. We should extend them to non-supersymmetric solutions. And then there is also a very important measurement problem, understanding whether these solutions are what is called typical or atypical state, and what does exactly mean by observing something, even the ring down in the fuzzball proposal, which is still, I think, an open problem. So if you're interested, we can discuss further this topic in the discussion. Okay, so I'll finish here, and thank you for the attention.
Thank you very much, Paolo. So I'm going to applaud on behalf of the audience. So we have a few questions. I think I first saw a question by Che-Yu Chen from the audience. Go ahead, Che-Yu.
Yes, thank you very much for the very nice talk. So I have two naive questions. The first one is just a confirmation. So in your slides, you have several embedding diagrams. So my question is that, are they already a collection of microstates or just a single microstate?
No, so these ones are not microstates. These ones they were showing are just vacuum solution of Einstein equation, which are deformed. The one that are microstates are these three. We have more, but yeah, we focus on these three. And this is a single microstate. So this one is this microstate with these three centers aligned this way. This is what is sometimes called scaling solution. These are centers on an isosceles triangle. But yeah, in general, for generic centers, I mean, one can put the centers to obtain regular solution, and yeah, there are different embedding diagrams, but each one for each microstate.
Okay, and the second question is that in your case, you only consider some perturbation field, and if you want to go to gravitational perturbations, then is there some kind of modified Einstein equation for you to perturb, or?
Yeah, definitely. It's much more complicated because in principle it's doable because the equation are known, is n equal to supergravity. The problem is that in 4D there are 3 or 4 gauge fields and several scalar fields coupled to gravity. So when you consider gravitational perturbation, you should also perturb all these gauge fields and scalar fields. So the equation becomes immediately very complicated, but in principle, it can be done. It's just technically challenging.
Thank you very much.
Okay, thank you, Che-Yu and Paolo. So next, Shinji, go ahead.
Yes.
Go ahead, Shinji, we can hear you.
Yes. Yep. Okay, so thank you very much. Very nice talk. And so I want to ask whether when you compare the quasinormal modes for the black holes and the fuzzballs, are you considering a non-extremal case or extremal case?
Here it's the extremal case. So this, in this case, these are fuzzball, which are microstates of extremal charged black holes. We are currently actually, I should have written, we are currently working with Taishi and Daniel Meyers to extend these to non-extremal black holes, because recently there was this paper, this paper here, I think, that extended some of these solutions to the non-extremal case. And in principle, the very same formalism and methods can be used also in this case. Yeah, we have some preliminary results, but they do not change qualitatively, I would say.
I see. But in the case, in the non-extremal case, do you expect that the fuzzball may collapse to form a black hole, or do you think that stays as a fuzzball?
So we again are doing only test fields, and we don't see any instability there. Concerning the gravitational perturbation, I don't know, but
because in the non-extremal case, we don't have a balance between gauge force and gravity.
Yes. Yeah, I don't know. In fact, it would be very interesting to study. Yes.
I see. Yeah. Okay. Thank you.
Okay, thanks, Shinji. Luciana, go ahead.
Hi, Paolo, that was a very good talk. Thank you. I have a couple of questions. When you want to couple the idea of fuzzballs with matter, and the first one is about, you're going to have accretion. So matter will interact with these solutions, and I would, since there is no horizon, you will probably, allow matter to get in and maybe still produce some emission. Do you have an intuition about how this would, differ from, let's say, a boson star? And the second question, which is related to this. Yeah, sorry.
No, go ahead.
Once there is enough matter, then, you may trigger collapse. So is it clear whether, the asymptotic state of any fuzzball anyway in an astrophysical scenario is just a black hole?
Mm-hmm. Yeah, so concerning the first question, the intuition would be that, it's not very clear to see it here, but one can imagine that all these centers are like point masses, so to speak, so they have their own gravitational potential. And the particular solution that is formed is such that there is a lot of, there is a big potential well within these centers, which is the reason why the signal does not die off, and is very complicated, because essentially radiation goes inside here and it starts being reflected and goes back and forth and eventually goes out. So I would expect accretion also to take or any radiation to be emitted to take very long time because of this, because it's trapped. Essentially, it's effectively trapped. Concerning your second point, I think it would be, the picture is, as you said, that eventually this matter will go there and can accumulate and maybe collapse. That's a possibility. Another possibility could also be, and is related to this very last point that I was, is related with essentially the measurement problem, because there are studies and arguments to say that because there is a huge number of microstates in this model, in principle, the effective reflectivity that right now is zero, because I'm just taking a single microstate, so there is no horizon, as you said, so there is no reflectivity. But if you start having many microstates which are very close in energy, any radiation might be absorbed just because one microstate will sort of jump to the other level, right? Like a very dense hydrogen atom. And in that case, in principle, the reflectivity can be large, and therefore this will change both the accretion, because, there'll be absorption, but of course, at the same time, it will change this picture as well, because it will behave even more like a black hole. So not only because of the compactness, but also in terms of accretion. Unfortunately, there are very few studies that quantify this effect. There are ideas, but I think it would be very important to understand.
Thank you.
Okay, wonderful. Thank you very much. I don't see any other questions, and I think we're just on time. Perfect timing. So let's thank Paolo again. Yes, thank